Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Beth.
Hello. Hi.
Beth was a student at Oxford. Beth's now graduated, but still a mathematician and is keen to come back and tell us about maths, which are
Yeah.
fantastic. Great to have you on the show, Beth, and great to have people at home who are joining in with Oxford Online Maths Club, for example, by joining in with the chat. I can see at the moment we've got people joining the Slido, like Aaron here, who says hello. Hello, Aaron. Chat today is moderated by Mario, who's a student at Oxford. Say hi to Mario in chat if you like, and say hi to Beth. There's Mario. Oh, there's Mario at the top of chat. Hooray! Name slightly spilling into the slightly overflowing, but we can fix that. Right, good. I normally ask them how their day's going. I'm going to ask Beth as well. Beth, on a scale from 1 to 5,
One to five.
1 to 5? Have we used numbers?
Oh, it's gone up to five now. I've joined this call.
Right. Okay. That's it, ever increasing, and it's kind of got nowhere to go from there unless it loops back around again or something. I'm always watching out for people who are having a terrible day, but have decided to find out about maths anyway, because that would be nice.
Might make it better. I don't know.
You never know, right? And also people who are having a 4-star day, which could maybe be a 5-star day. Who knows? Good. Right. So we've got some clocks on the screen without any hands at the moment.
I can tell you all about them whenever you're ready.
I'm very excited for the secret codes as well. Right, I'm giving them a moment to let me know that
Yeah.
this is the point where somebody would potentially tell us that we've done this completely wrong. Hamish is here. Hamish says hello, glad to be here. Bob's here too, and Joe, and Mario from chat. This is where someone would tell me that I've forgotten to unmute myself or something.
Sure.
Or forgotten to unmute you, which would be quite rude. I think we're good. I think chat's having an okay day. 4.1. I'm going to pause the voting there, I think. Good to know chat's happy for some maths.
Cool.
I think I should just hand over to you to explain maths clocks, the weird world of mathematical time telling.
Sure.
There's points where chat can join in, I think, so we'll try and get chat to join in as we're going along. And as always, chat, if you want to interrupt or ask questions or just chat, then that's what it's there for. So do get involved. But over to you, Beth.
Yeah. So I want to tell you about my favorite area of maths, which, well, it's called modular arithmetic, but really it's about weird math clocks. So yeah, we'll see how time telling can get kind of weird and see how we can use it to maybe send some secret codes to each other. Yeah. So before we start talking about weird math clocks, let's go back to our standard clock and think about how we tell the time normally. So when we tell the time, we wouldn't say, for example, 16 o'clock. In our heads, we know that if we see like 16 on a digital clock, we know that means the same as 4 o'clock. So in our clock world, like 16 and 4, same thing. So we're going to say that 16 is congruent to 4. So 16 and 4, basically the same thing in clock world. That's true for other things as well. Like we wouldn't say 21 o'clock normally. In our heads, we know that's the same as 9 o'clock. So 21, 9, same thing in clock world. Yeah, but perhaps, well, oh yeah, I'm trying to think how people think about this. Like when you're imagining that in your head, you might like imagine like the numbers from 13 to 24 sort of like overlapping the clock might be a way you think about it. If you hit next, James, you might see a beautiful animation of that. So maybe you're thinking about like the numbers where they'd appear if you kept counting round after 12 and like 21's next to 9, so 21 and 9 are the same thing. Um, so that might be one way you think about it. Um, so what about if our time went above 24 hours? So if we start thinking about slightly weirder worlds, what would 26 o'clock be on this clock? If we have a think, well, 24 is by the 12, 25 would be like by the 13 and the 1, so 26, if we count round, would be by the 14, by the 2. So 26 would be 2 o'clock. We wouldn't say 26 o'clock, we'd say 2 o'clock. I know this is all a bit weird, but bear with it for
I really wouldn't say 26 o'clock, but I guess if somebody said it's 26 o'clock, I'd think
you would panic.
I'd panic,
Well
but I
blended.
guess I would start counting around on a clock to find out what they meant.
What they mean.
And you
And
keep
hopefully you might
going.
end up with 2 o'clock.
Okay.
Yeah, kind of interesting. We're gonna make I could say another way we could think about it at this point is another way to imagine it is 26. To get to 26, you go around like 12 twice and then you add 2.
Yeah.
So the remainder, when you divide 26 by 12, is 2. So we could also think about remainders when we're trying to work out what times are the same as each other. Say 16, when you divide it by 12, the remainder is 4. You count around 12, you go on 4. 21, you divide by 12, count around 9, from 12 on the top of the clock. So we can also think a little bit about remainders. That might be helpful.
Sure. I guess they've got the same remainder when you. Well, no, hang on. Yes. Okay, they've got the same remainder when you divide by 12, haven't they? That's the thing that they've got in common. Cool. Okay. That's how I understand why 26 o'clock. I think. Yeah. Okay. What would it be? What would it be if it was between 0 and 12 or something?
Yes. Exactly. I guess yeah. So one little change we're going to make about our clock is we're going to remove actually the 12 on the top and we're going to replace it with a 0. If you hit next, James, we'll see a little change happening. So we're going to replace our clock. So we won't talk about 12. We'll talk about we'll say 12 is congruent to 0. So all the numbers on this clock and beyond are congruent to something in the range of like 0 to 11. And we want to be super clear that we're talking about our normal everyday clock with 12 numbers on it. And so we're going to say we're talking modulo 12 and that all these congruences are true mod 12.
I see. So I saw on your title slide that you have other clocks with other numbers on them. So this is a kind of clarification in brackets?
Yes, a clarification in brackets that I mean this in the 12 clock world, no other world.
Which we're calling modular arithmetic, sometimes written modulo 12, or this thing in brackets mod 12. And this equivalent sign, I guess, might be new for people, maybe not.
Yeah, it's equal signs with a third line, kind of fun. So yeah, we call that like a congruence, or would say like 16 is congruent to 4. So it might be a new symbol to add to your toolbox.
I think I'd feel silly saying that 16 was equal to 4, but if I say it's equivalent to 4, then, or in this case, I guess you're saying it's congruent to 4. Like, where have I heard that word before? Chat can help me. So I've heard it in the context of this sort of stuff, the word congruent, but I think I've also heard it in geometry for congruent triangles. Is that a thing? The congruent triangles are ones that are basically the same. They might be in different places. There might be different orientations or something, but they're sort of similar in some way.
Yeah, interesting. Yeah, similar sort of
similar shapes.
Yeah.
Says Hamish in chat.
Yeah.
So this is why there's a remainder function in Python, says Joe, that is also called modulo.
Nice. Modular arithmetic is used in a lot of coding languages.
Those are related concepts. Right.
Yes.
Okay.
Let's have a look at what it might look like if we have clocks with different numbers on them. And let's make things weird. So if we talk modulo 5, we can imagine a world where clocks just have 5 numbers on them. So if we think about the number, say, 6 in this world, well, our clocks only, have 1, 2, 3, and 4 and 0 on them. So where would 6 be? Well, if we count round, so we've got 0, 1, 2, 3, 4, 5 would be on the top, 5 is congruent to 0, and we'd count round 1 to get to 6. So in the world, in our 5-sided clock world, 6 and 1 are basically the same thing. So 6 would be congruent to 1 modulo 5.
Okay. Those things have definitely got the same remainder mod 5. Their difference is a multiple of 5 is another way of saying it, because you've gone around the whole clock a certain number of times, in this case an extra one time. So if their difference is a multiple of 5, then they say, well, They're not the same number, but they're
Yeah.
they've got something in common.
Yes. Um, should we think about 8 on the clock? Where would 8 be?
Yeah, it's tempting to say it will be over by 4 because 8 is twice as big as
Isn't
4.
it?
Um, but I suppose maybe I should do the counting, shouldn't I? Chat can play along at home, pointing at the screen. 1, 2, 3, 4, 5 at the top, and then
Yeah.
6 is congruent to 1, 7 is congruent to 2, so there's 8 congruent to 3.
8's congruent to 3. So yeah, we can think about that like the counting, or we could think, okay, the remainder when we divide 8 by 5 is 3.
Right.
Very
Or
nice.
again, they've got. I guess looking at them now, they've got a difference of 5, so their difference
Yes.
is a whole number of times around the clock.
Yes, I like that. And then 5 in this world, what would 5 be congruent to?
Yeah, Bob told me 3 in chat for the previous one. Anybody in chat want to tell me where would 5 be on this clock that
Yeah,
weirdly
maybe
has a 0?
really has a 0. So
I did. Yep. An anonymous person has got in first. Oh, I forgot
okay,
some. They can be anonymous in chat.
so yeah, we
Maybe
would
she's not
say
listening.
5 is just congruent to 0. Beautiful. So yeah, we've talked modulo 12, we've talked modulo 5. We can have clocks of any number of sides. If you hit next a couple of times, James, we've got modulo 7 there. So that would be a 7-sided clock, but we could have like a 93-sided clock. We could have modulo 93, we could have modulo 1001. You can go as crazy as you like. I feel like any positive number, you can make it a modulo and think about the clocks related to that. Yeah, so hit next again, James. And there are a few other things to think about here. So maybe for chat to just have a 30 seconds, a minute or something, just to have a think about some of those and see what you think. So the first one is 5 mod 3. So that's where 5 would be on a 3-sided clock.
I think it takes about 20 seconds for stuff to get out to chat, for people to
And
stop it
then
and come back again. And
come
what I
back.
want to say, if you're currently typing and in your world in the future somebody's pressed enter already, just keep typing, just go for it. I don't mind
Yeah.
if you all agree. I don't mind if you say the exact same characters as somebody else. You're producing some amount of work for Mario, who has to press OK on these things, but that's all right.
Quick fire.
And to be clear, Mario is not checking that your answers are correct. Mario is here to make sure people are well behaved and not dividing by 0.
Beautiful.
Good
We've
stuff.
got
Thank you, everyone.
many answers.
We've got many answers. I've forgotten the
nice.
questions.
Cool. So 5 mod 3. If you hit next,
Ooh, are
James.
they on the slots? Okay.
Oh yeah, no, it's
Oh, my
fine.
goodness.
Yeah.
There we go. Look at that. Oh, there's a 3 clock.
It's a 3 clock. So yeah, as usual, we can count round. We'd see that 5 would be next to 2. Go 3, 4, 5, or we can think about remainders or differences when dividing by 3. And then the next one, modulo 7, where would 15 be? Well, 14 is divisible by 7, so we'd count round one more to get to the 15.
Oh, there it is.
That one.
14 and 15 is there. The
Beautiful.
difference is a multiple of. So, okay, got it. Yeah. I've got my.
And then this last one, you might not want to be counting around loads and loads of times.
No.
So we might want to think a little bit more cleverly here. So mod 5. So this is a 5-sided clock, and every time we reach the top of the clock, we're hitting multiples of 5, right? So it would be like 5 would be at the top, and then 10 would be at the top, 15, 20, and so on. So I know that 250 would be at the top, so then I can count round an extra 3, and I know that it would be 3 mod 5.
Okay. Right, so this is the same sort of thing as asking people about remainders at the moment.
Yes, for now it is. Let's see some other ways of thinking about modular arithmetic that might help with some other kind of questions.
Is it time for the big animation?
Oh, it might be time for the big animation.
Okay, right.
Let's see if we can get this working.
If you're wondering why the slides are better than normal, it's because I have Beth. Beth has,
We'll be carried away with an animation.
Beth has tried, I would say, at least one order of magnitude more than I've ever tried making slides for Maths Club. Right, let's hope. I hope this goes over YouTube. Here we go.
Cool. So I think hit next once more.
Okay.
Okay, so we're going to imagine another way to talk about modular arithmetic. So it, so we've got our usual, so we're talking modulo 3 here. So we could imagine coiling the number line. So we've got our normal like 0, 1, 2 on the clock for our three-sided clock, and we can keep coiling that number line up and up and up. And we can also coil it down with the negative numbers. So yeah, if you see there, we loop round from like 0 to -1 to -2. And what you see being beautifully animated are these columns of congruences. So everything in the columns are congruent to each other. So in that middle column, we've got 0 is congruent to 3, it's congruent to 6, all these things in that column, they're like the same thing in three-sided clock world. And same goes for the columns of ones, everything in that column, they're all basically the same as 1. And this is quite a nice way to think about modular arithmetic because it allows us to think about negative numbers. So we can also talk about negative numbers in modular arithmetic. So here we can see that -2 is congruent to 1. And I guess you could, there are so many ways to think about this. I think another way James was mentioning was like adding and subtracting like multiples of 3. Say like from 1, if you subtract 3, you get to -2, and you add 3, you get 4, and add 3, you get 7. And that's another way to sort of help you know which ones are the same as each other.
Yeah, I guess something I've spotted on this picture is that 2 and -2 are totally different. They're in different columns.
They are in different columns.
Tricky things about counting. I think someone maybe do this. It reminded me of a challenge or something. You get people to count backwards in tens starting at 27 and keep going.
Sure.
And people tend to say 27, 17, 7, -7, -17, and that's wrong because of this, right? That if you subtract, in this case it's 3s, but if you subtract minus 3, you don't get to -2, you get to -1.
There's definitely an element of having to like sort of sort of erase your preconceptions about what like how you think maths normally works when you're talking in different clock worlds.
Yeah, although I've remembered that I brought this up as a kind of profound thing, but possibly people watching at home know that minus signs matter in normal maths as well. Like it's pretty rare that you get to ignore all the minus signs. So that's also true here. Are we going to say, so I've sometimes seen people write the equivalent sign kind of both ways around. So if 6 is congruent to 0 mod 3, I've also seen people write 0 congruent to 6 mod 3.
Totally right.
Is that okay?
Yes, that is fine. So a nice thing, a good thing to remember really is that while we normally compare things to like that base clock, we can say 3 is congruent to 6 mod 3, or 10 is congruent to -2 mod 3, or 1 is congruent to 10, or 10 is congruent to 1. We can sort of play around with numbers within those columns and say they are congruent to each other in whatever way we like. I think if you hit next, James, is that maybe what the next slide says?
Possibly,
so,
sorry.
You let me in beautifully. Oh no, it isn't, but
yeah, so this is what is 5 mod 3. Sorry if I
Oh yeah, so we can hit through. These are just some different ways we could think about it. So we've got our clockway, we've got our spiral. If you that's okay. Clock, spiral, we've got remainders. And there is another way of thinking about it, which is sort of a formal definition-y way, which I think is most helpful if you start exploring modular arithmetic more and end up wanting to like do proofs and things in it. There is a sort of technical way to write out what we mean by things being the same as each other. But for now, we maybe won't worry about that, and maybe James can link to it in some extension bonus sheet.
I'll put some things in the further reading notes. Which, quick plug, I do further reading notes. It's like a blog post the day after the live stream of all the things that we didn't have time to say. It's this phrase is divisible by 3 that I found people have problems with. So I'll put some stuff in the further reading about what it means to be divisible by 3. Possibly you already know it at home, but possibly you will find my opinions about what it means to be divisible by 3 alarming. Which is why I'm not going to share them here. I'm going to put them in my blog post.
I'm very excited now.
I think you'll be fine.
Trees. Okay.
It's this stuff, right? So I've seen it's this. Is it ever okay to write 2 is congruent to 5 mod 3? Because you
Yeah.
can't say that, you can't really say that 5 is the remainder because it's too big when you divide by 3.
Yes.
But you could say that anyway. Never mind. I'll put it in the further reading.
Okay. Yeah. That sounds good. Hit next, I reckon. And let's see. Oh yeah, this is sort of what we were saying earlier. So yeah, we can say anything within these columns are fine. So 5 is congruent to 8 mod 3, and so on. Even though we would typically compare it to the base circle, we can play around a bit, and that's all valid maths.
This one's my favourite, I think. The kind of tautology one. 5 is congruent to 5 mod 3.
Just a sense
Was
check.
anyone in chat? Did I see this earlier? Was anybody in chat willing to just go, these things are congruent to themselves? I'm not sure anyone put it in chat, but on the challenge
yeah,
where
sure.
you were
When I was
read it,
earlier saying like, what is this mod 3? You could, there is a range of answers you could give.
I'd be happy with that. 253 is congruent to 253 mod 5.
So wait to, smart out some teeth.
Good. Okay.
Stunning. What have we got next?
Useful property, I think. I'm looking at your next slide.
Useful property. Fun. No, it's great. It's a surprise to me. I mean, I made the slides, but I've forgotten. Cool. Let's reach our first useful property about modular arithmetic that we are going to be using lots for the rest of today. So this theorem says, if a number x is congruent to a number a modulo n, and y is congruent to b mod n, then x times y is congruent to a times b mod n. So yeah, the thing with maths theorems and properties and so on are they often look very confusing to read. But what this theorem is saying, if we have 2 bigger numbers, if we want to find out what their product is, modulo n, instead of multiplying them together and then working it out mod n, we can work out what those bigger numbers are, mod n, make them smaller, and then work out that product, modulo n. Nice. So maybe we can illustrate that with an example better.
Right, sorry. Okay, yes. Multiplication works. So, okay, so you've got a challenge for chat. It's 5 times 13, but you only want it mod 4. Mod 4, yeah. So I guess if you're thinking about remainders, there's only a handful of possible answers for the remainder.
Yes, so we know the answer for this is only going to be 0, 1, 2, or 3, which is quite nice. It means, you've got a 1 in 4 chance of getting this right, actually. It's quite good.
Okay, let's try and do better than 1 in 4 guesswork. So I guess chat has the option, because I reckon chat's probably quite good at multiplying together numbers. They could go and work out 5 times 13. So
you could do that and get the, a reasonably big number, not that big.
Yeah, maybe it's 253, who knows? And then take 253 or something and think about that mod 4.
Yes.
But
we've got some answers coming in. Interesting. So yeah, so what this property means we can do is, instead of doing 5 times 13 and working that out mod 4, we can be like, what's 5 mod 4? That's 1. What is 13 mod 4? That is also 1, because I guess 12 is divisible by 4, and you just count around 1 for 13. So both of those things are congruent to 1. So this property, or this theorem, says if we multiply those smaller numbers together, we will get our answer. So 1 times 1 is just 1. So by some magic of this theorem, we know that 5 times 13 is congruent to 1 modulo 4. Nice.
Cool. Okay, which I think is also true if you work out 65, he says, frantically multiplying.
I know, yeah.
People in chat are putting, yeah. I'm not great at multiplying numbers together. Let's find out. Oh, I've put your next one on the slide. It's nice. 132 times 14 mod 7. Yes.
So again, we can think similarly. Here we've now got, a 1 in 7 chance of guesswork being right. So slightly less favourable odds.
Well, so you would quite like, to be clear, you would quite like something between 0 and 6 inclusive.
I would, yes. Before we get any.
For me, it would be acceptable. I think, to say, well, that's congruent to 132 times 14, or 14 times 132. Like, you can sort of with my way of working, you can kind of opt out. But if we're requiring them to come up with a number between 0 and 6 inclusive.
Yeah. So this is quite a fun demonstration of this theorem because, well, we could work out 132. Well, first of all, we could do the whole thing, multiply it together and whatever, but that's a very big number. I like to make my life easy where I can. 132, again, I could work that out, mod 7, but actually, if I look at the other number here, we've got 14 in this multiplication. 14, I know, is divisible by 7. And as I think a few people have noticed in chat, 14 being divisible by 7 means it's at the top of the seven-sided clock. So that's 0. So 14 is congruent to 0, and anything times 0 is 0. So what 132 is modulo 7, I don't really care. It could be anything between 0 and 6. Doesn't matter because it's times by 0, and that means it's going to be 0 mod 7.
We've got a sequence in chat from Bob, Aaron, and Coyle that goes 0, 0 with a question mark, 0 with 2 question marks. You're all correct. 0, brilliant. Which means you don't actually need to decide what 132 is, what the remainder would be when you divide that by 7. It doesn't matter. You could leave that as 132 if you like. Anyway, this is a good sign. Good news, you are allowed to multiply by 0 on this show. We have a rule that you shouldn't divide by 0, but multiplying by 0 is okay. So keeping chat moderator Mario on his toes. Okay, good. What next?
I reckon it might be time to jump to the mirror board.
Oh, right, okay. I know how to do this.
Let's mix things up.
Let's go here. No, wrong. Click
here. Commercial ad break.
Almost there. Oh yeah, quick ad break.
Ad break.
Ad break. We've got 3. Hi everyone. Promise Europe is a thing. If you're hearing about it for the first time, put it in a search bar or something to find out about Promise, or watch the introduction to any of the last few videos where I've been mentioning Promise Europe at the start. There are previous videos from Maths Club. That's right, it's an ad for Maths Club in the middle of Maths Club. Also, Beth has a YouTube channel. Do you want to plug your YouTube channel quickly?
Oh, yeah.
What sort of stuff do you do?
Yeah, cool. I've got a YouTube channel. It's called Maths Unboxed. I do various videos on both sort of like school level, A-level maths, but also introduction into areas of university maths. And I actually have quite a lot of videos related to modular arithmetic. So if you're interested in the stuff we're talking about today, go check it out. Woo!
Woo. Thank you to Joe for posting 0 with 3 question marks. They know a pattern when they see one. Nice. Right, okay, that's the outbreak. We've got challenges. Cool. We've got a useful.
Let's do some spicier questions. So we're going to keep using this idea that modular arithmetic is really cool for multiplying like big numbers, as we can break them down into their smaller components and multiply the smaller components, and we love that. So our first fun challenge is this question, which is, what is 5 to the power of 34 mod 4?
Sorry,
which is a bit scary.
Are you asking them to multiply what?
It's a big number, isn't it?
So we've gone from multiplying together 2 numbers to doing 5 to the power of 34. How's chat doing?
Big number.
Yeah.
I know, I'm hoping for some supercomputers around. But with modular arithmetic, maybe it's not so bad. What do you think?
One with increasing numbers of question marks. They've found a thing.
Nice.
Please don't make this the thing, chat. Although it's a long-standing tradition. One of my current students admitted to me that she's currently a student at Oxford. She's smart. She admitted that she would post in chat with her name if she was doing a sort of joke or just having some fun, and she would post anonymously if she was answering a maths question. So that I just think that's sort of like split between 2 identities. There you go. 34 5s.
So,
yes, all of which are basically a 1, says Hamish.
Yeah. So 5 to the power of 34. Got to remember, it's the same as just saying 5 times 5 times 5 by itself, loads of times, 34 times. And by our lovely theorem, our useful property, we can reduce each of those like things in the multiplication mod 4 and then multiply that together. 5 mod 4 is 1, very conveniently. And we love 1s, -1s and 0s when we're doing multiplications because those are easy multiplications to do. So this is congruent to 1 times itself a bunch of times, mod 4. And notice we've suddenly entered 4 clock world. So the congruent sign, our triple equal sign comes in as well as the brackets. And that is just equal to 1. So
Can do 1 to the power of 34, even in
yeah,
the weird maths clock world.
Indeed. 1 to the power of 34 is significantly nicer than 5 to the 34. So yeah.
Cool.
Nice.
Is there a second challenge?
There is a second challenge. Da, 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 da.
Everyone says challenge 1.
Oh no.
Oh my goodness.
This one. Right, this is phrased a bit differently. This says, what is the last digit of 7 to the power of 100? This is pretty mean.
So,
I don't love the 7 times tables. It's one of my least favorite times tables.
I'm not going to multiply out.
Don't love them.
I guess the only thing I'm thinking is that I could try and look for a pattern. I could try working out the last digit of 7 squared, the last digit of 7 to the 10. Wait, I'd probably do 7 cubed next, because 7 to the 10 is huge. When you say last digit, is that...
Yeah, it's interesting. So this isn't explicitly a modular arithmetic question. I haven't included the word modular or modulo or anything in this question. But is it a modular arithmetic question in disguise? So you're totally right. In general, if we didn't know about modular arithmetic, I think a really good way to tackle this question would be to look for patterns and do like 7 squared, 7 cubed, 7 to the 4, look at the last digits and see if we can work something out. Totally valid approach. Let's think about what the last digit means. I guess it's true that, let me think.
It's a mod 10 sort of thing. Maths 22222 has put something about mod 10 in chat.
Oh,
so
nice. I like that. So
Um,
yeah, say we've got like, I'm just picking a random number, like 273 or something. It's true that like any number we can write as some number like multiplied by 10 plus the final digit. I don't know if that's a confusing way to think about it.
That's right. It's place value. They can do place value. So I think it's the
Yeah.
So in my world, yeah. So in my world, if the difference there's a multiple of 10 on screen. So if I think about the other two things as having a difference that's a multiple of 10, then I'm cool for those to be congruent.
So yeah, working modulo 10, we just get like anything times by 10 is 0. So we would just get like the unit place of the number. So it's a bit of an interesting place value sort of question. But if you think any number, when you get to like the top of a 10-sided clock, when you count round, you would get the unit value of that number. So finding the last digit is equivalent to working mod 10, which is quite nice, I think. And once we have that kind of modular arithmetic language, this question becomes the same as, what is 7 to the 100 mod 10?
Yeah. Anonymous in chat has done my kind of, well, probably it was their idea that happens to coincide with my idea, but looking for a pattern, they claimed that every 4th number, so when you do 4 of these things, and it ends in a 1.
Nice.
Aaron has worked out the first 4 powers of 7, and I just want to tell Aaron that probably you're allowed to throw away quite a lot of those digits. Kind of the only thing that matters is the last digit. So while you're working out 7 to the 4, I think it'd be okay to throw away things except the last digit. Felicity says, oh, I saw you were Felicity and then you changed to Anonymous, sorry. Anonymous says, I did my best. Anonymous says, why mod 10? And which is a fair question, because there's no 10s in the question. I think it's that relationship between when people say the last digit in the decimal number system, the last digit is the remainder after you've written down all of the multiples of like 1,000, 100, if there's a million there, until you've just got the last bit left over. The kind of final place value on your number is the bit that's not a multiple of 10. Everything else is kind of made of something that ends in 0. It's like this huge number what are you writing down there? 10,324. The 10,320 bit is a model of 10. So if you just want the last digit, that's the same thing as getting rid of all of the multiples of 10, or saying how many times would you go around the 10 clock? How many times would you go around the 10 clock? I don't care how many times you go around, actually. I just care about the remainder, to say, after you've done that 1,032 times or whatever, you've just got 4 left over. Mod 10 is this bridge to...
Neat little thing that last digits, modulo 10. It's always a neat little trick to look at. But yeah, it just takes some getting your head around. So I like all the methods in chat. Let's have a think about the modular arithmetic shortcuts. So 7 to the 100 is the same as 7 times 7 times 7, 100 times. What I might try and do is we could also write this as like I could bunch them up basically. As in like I could bunch up pairs of 7s. And so I could also write this as like 7 squared. This might sound a bit strange, but a bunch of times, 50 times, in fact. Why am I doing that? So actually, if we think of powers of 7 in modular arithmetic, so 7 mod 10 is just 7. 7 squared mod 10, well, 7 squared is 49. So modulo 10, I guess it's at the top of the clock, so we count round and we get our 9 mod 10. But it's also congruent to -1 mod 10, which is quite fun. And we always want to look for 1s, 0s, and -1s when we're doing these kind of power questions because they're fun to multiply.
I can do big powers of -1, and you've got over there something that's congruent to -1 50 times.
Exactly. So we've broken up the like big powers of 7 into smaller sort of subsections of these powers of 7, and 7 squared is a nice one because that's congruent to -1 modulo 10. So this is actually congruent to like -1 times itself 50 times.
This works. This works in general, doesn't it? So if I'm thinking about powers of 13, but powers of 13 go 13 squared is 169, and at that point I've got 1 less than a multiple of 10, so I'm congruent to -1 mod 10.
That's quite nice. It won't be true for everything, will it?
Not true for every number, fine, but I can think of other numbers it works
other
for.
ones. Yeah.
So 19 is already -1 mod 10. So if I'm doing powers of 19, then the pattern is a little bit different. I'm kind of thinking, can they explore this for other values of 7?
I mean, say you'd got 7 squared equals 9 and you hadn't thought about -1, that would have been okay. You could have gone straight to like, you could have done 7 cubed and then maybe 7 to the power of 4. And you'd have found that that was congruent to 1 mod 10. And you could have done 1 times itself several times instead of a -1.
I think that's more common for what people were doing in chat.
Yes. But nice to throw in a little minus. Do we want to do challenge 3 or should we keep going?
Let's put it on the screen so that people can think about it.
Yeah.
Ooh. Okay, so remainder when I divide by 7 means something about mod 7, and it's some humongous power, 25 to the power of 20, 25.
So this is another question that's like modular arithmetic in disguise because it's talking about remainders. So as soon as you see remainders in a question, you got an alarm bell should go and be like, I can whip out my modular arithmetic toolbox for this. So this is the same as 25 to the 2025 mod 7. But I think let's skip that for now. And that's something chat can think about in the background or when they get a bit of time later. And likewise, some other interesting things just to mention in passing. Modular arithmetic is really cool for proving a lot of number theory things, such as that nice trick when you add up the digits of a number, and if the digits are divisible by 3, then the number itself is divisible by 3. Modular arithmetic has a super nice proof of that. So some interesting other things to explore afterwards if you like I do actually have quite a good video on that one.
We did the outbreak already. I used the 4003 thing. And I've used that in a test question at some point, I think. We
Nice.
put some stuff in there as well. It wasn't a question really about modular arithmetic, but
Let's follow this
we
arrow
used
and see
that
what.
fact.
Nice.
Oh, Fermat's little theorem.
Woo!
Hello.
Let's. There's a fun theorem in modular arithmetic. This is called Fermat's little theorem. Not to be confused with Fermat's last theorem. That's a very different thing. This is his little, much more manageable theorem. And it says if P is a prime and A is co-prime to P, so co-prime meaning they don't have any common factors. So like 3 and 10 are co-prime. They don't share any common factors. 3 and 12 are not co-prime. They both are divisible by 3. Anyway, if P is prime and A is co-prime to P, then A to the power of P minus 1 is congruent to 1 modulo P. What on earth does this mean? So I guess, say we were working with like powers of 2 modulo 7. Sorry, maybe modulo 17. Let's see. So say we're working powers of 2. I mean, anything's fine. I'll just go bigger numbers. So
I could work these out, couldn't I? Because they're 2, 4, 8, 16. Or you're going to work them out, sorry.
Oh yeah, no, I was just going to say, yeah, so just say you have a question like involving powers of 2 mod 17. We can think 17's a prime and 2 is co-prime to 17. So this theorem tells us that if we make 2RA, then 2 to the power of 17 minus 1, which is 16, is congruent to 1 mod 17.
That's mad. 2 to the 16 is 2, 4, 8, 16, 32. About 33,000. So
exciting. So we can check. I like
32,600 so 32,760.
Whip out the calculator and check.
So you're telling me 32,767 is a multiple of 17? Seems possible, but unlikely. But I suppose I can check using the tricks we were doing before, right? So chat can maybe check, because I think the powers go 2, 4, 8, 16, at which point you have 16, which is one less than a multiple of 17. So then, 2 to the 8, I think, is also 1 mod 17, but I'm not sure.
Nice.
I can check that one. 2, 4, 8, 16, 30, 64. 128 is 120. What am I doing? So I just looked to the side and saw my reflection in the window and thought, what on earth am I doing? If you prove this, then you will be following in the footsteps of Fermat, who is a mathematician in the "Oh gosh, why have I started this sentence like I can remember Fermat's date of birth?"
Oh no, 1700?
Yeah. Sure, let's go with that. Who did many interesting things in number theory, including this one: true for all primes P and all numbers that are not multiples of those primes P. Or sorry, that are co-prime to P. There's a thing on the board as well with a cursor over it, but you've got a thing with 4 and 11 going on as well.
4 and 11. Oh yeah, I was just going to show you how we could use that in like in a sort of kind of the same sort of questions we were doing just before. Basically, Fermat's little theorem is a bit of a shortcut for us. So if we're looking at a question where we're saying, well, this question is actually in disguise, it's saying, what is 4 to the 532 mod 11? And we could do what we did before, and we like group up powers of 4 and try and work out which ones have got like a 1 or a minus 1, and then times that. We can shortcut it slightly. Now we've got a new fun theorem in this case because 11 is prime and 4 is co-prime to 11. So we can say straight away by Fermat's little theorem that 4 to the power of 11 minus 1, which is 10, is congruent to 1 mod 11. So instead of us trying to find a good power of 4 to use in this question, Fermat's little theorem just gives it to us. It's lovely. So
this tells us that the sequence, if we're working out powers, mod 11, the sequence starts repeating, or maybe it's already started repeating.
Might have already started repeating. So this might not be sort of the best case this theorem's giving us, but
right,
it's
like
giving us a nice
2 to the 8 is 1 more than 1 to 17 in the previous one. But this does is that it's going to start repeating at some it's going to be repeating.
Yeah. So this makes like questions like this one a lot nicer, I guess. You can think about it a bit more later, but I guess I could write this as like 4, so 4 to the 532, I guess, is the same as like 4 to the power of 10, like to the like times by itself 53 times by an extra 4 squared.
Be honest, are you doing modular arithmetic there? Are you doing
I mean
modular arithmetic
that is just
inside?
normal math.
I think you've taken 532 and worked out what that is mod 10. I
Um,
think because look, you've split
uh,
it out into loads of tens, and then just the remainder is the two on the end, right?
is this on the end?
Yeah, I think you're
So
doing. Yeah, just that bit. Yeah.
so I guess this is like congruent to like 1 times itself loads of times times by the 4 squared at the end. What's that?
Yeah. So I'm not going to let Hamish use decimals here. I'm going to
Uh,
say the correct thing to do, I think, would be split it out rather than sort of optimistically hoping that if I let you use decimals like that, then you'll tell me everything is always one on the right hand side. Um, the true fact comes, I think, from splitting out those leftover two that don't divide neatly. That's why I'm saying modular arithmetic in the exponents as well. And then it turns out to be lovely 5.11. Nice. Which I've seen in chat with varying numbers of question marks.
Lovely. Great. Something. Should we follow the arrows and see see what else we have in
Where are we
store?
going?
Where are we going?
Is
I'm conscious of time.
quarter to 6, but I think we're doing good.
Okay. Yeah. We're almost there. We want to get
We
into
could
some
do some
secret
codes.
methods ending. So we'll plow through this so we get to the spy stuff. I just a sort of quick aside is that a new bit of terminology. If we have if A times B is congruent to 1 in some clock world or some modulo n, then B is the multiplicative inverse of A modulo n. And I guess it's true that A is the multiplicative inverse of B as well. So yeah, there's this idea that numbers can have an inverse, and that inverse exists when you multiply those numbers together and it gives you 1 in that world. So that example there is like 2 times 3 is congruent to 1 mod 5, because 2 times 3 is 6. So 3 is the multiplicative inverse of 2 mod 5. Yeah. Do we
So
want to
if you can multiply, so
Oh,
like
yeah.
I see. Okay. So if they multiply to give 1, which is like the identity. If you know about matrix inverses, then you've seen some sort of more general context where you've got inverses. We've got this in this clock world.
Often the sort of like, yeah, 1 is seen as like the identity in multiplication, and 0 is the identity in addition in some ways, isn't it? So
I don't know if that's helpful for people watching at home, but
no,
it was
maybe
helpful
not.
for me. People are attempting questions about finding
Yeah,
inverses.
through some questions and through some answers in chat even. So the inverse of 1 mod 7.
Well, hang on. When you
Maybe a
say
little
the
bit.
inverse of 1, you're looking for a number which, so if
Uh-huh.
A is 1, A is 1, you're looking for a number B such that A
Times
times
them
B,
together
you get
gives you
1.
1. This is a trick question. I'll just say it straight up. That's being mean. I think some people have written the answer. But anyway, the inverse of 1 is just 1.
Right.
Mod 7, that was a bit of a mean one.
Because 1 times 1 is 1. Welcome to the Oxford Online Maths Club.
Good facts tonight. Uh,
Good fact.
um,
What's the inverse of 2 mod 7?
2 mod
That's a
7.
bit harder, right?
Bit harder. So we've got to think like, yeah, what number would you multiply by 2 to give you 1 in clock 7 world? And I mean, the options for the inverse of 2 are going to be just like 0 to 6. We've only got 7 options for this inverse. So I guess you could just try them all out. I think a few people have written. So it's, 4 is the inverse of 2 mod 7. 2 times 4 is 8. And 8 would be next to 1 on the 7-sided clock. So the inverse of 2 is 4. Beautiful. And the inverse of 4 mod 5, I think some people have written. 4, yeah. 4 times 4 is 16. 16 is 1 on the 5-sided clock. And inverse of 3 mod 11. Even I'm not sure. What's that one?
So if
Um,
something is one more than a multiple of 11 and is a multiple of 3, I'm going to start looking at things that are more than multiple of 11s, like 12 is one more than a multiple of 11 and is a multiple of 3. So you go
I
3
feel
times
like
4.
the questions are misleading. It's not often four that's the it's not always four the answers to these questions. Um, I thought poor question choice from me. Um, and the inverse of 3 mod 6. Have we got any answers to that?
Sort of.
Sort
I've
of.
got
What do you think?
one vote for 0
Yeah,
and one vote for doesn't exist.
exists.
Well, let's check
Yeah, so
0.
if you loop through all your options for 3 mod 6, I guess like 3 times 0 is 0, 3 times 1 is 3, 3 times 2 mod 6 is 0. You can loop through all of them, and I don't think you'll hit 1. If you do 3 times 0, that's 0, and we're looking for 1. Um, so it doesn't exist. Trick question again.
Oh,
And that's fine. That makes sense. If we do a little scroll down, we can see this fun statement that A has an inverse, mod n, if and only if A and n are co-prime, so they don't have common factors, and 3 and 6 have common factors, so that makes sense that there wasn't an inverse. And if the inverse exists, it's just one. So we can talk about the inverse of a number. The inverse is unique.
I just warn you, I have a panic button under my desk for when somebody divides by 0, so that I can just like get out quickly. And I'm very close to pressing the panic button when I see this.
Got that number.
Like you're sort of trying to divide. You're sort of trying to divide by something that you can't divide by. So I'm like, oh, I haven't hit the panic button yet, but I feel like we should be careful. Somebody's asking about math. I'm going to type a response. There's a link that I can give them where they can find the information they're looking for. I will type that in Slido. Style points to Aaron for picking 8 for the first one. 8's congruent to 1 mod 7, so we're allowed.
Let's spend the last bit doing some secret code sending. One of the applications of modular arithmetic is cryptography, which is the area of maths involving sort of sending encrypting secret messages to send between people or machines. A really important area of maths. And cryptography is super important, undermines sort of the internet and how information is just exchanged securely online. So every time you do some sort of bank detail input online, likely modular arithmetic is being used behind the scenes. In particular, this algorithm called the RSA algorithm, which was created by 3 students. It's sort of a self-titled algorithm. They've used the initials of their names to form RSA. They became very rich after they realized modular arithmetic could be used to send secret information. Exciting. So let's have a look at how we can use it in a sort of similar way to what computers do, but we might use smaller numbers.
Just going to see if I can hide your cursor. Would you mind moving your cursor slightly?
Yeah,
just covering up.
absolutely.
As I say, sending secret codes to people. Sorry, it was
Yeah.
maybe part of the secret who you were sending secret codes to. Just people. Okay, anyone.
Oh yeah, sorry, it's a good point. It's anyone, or it could be between machines.
Right. Machines love primes. Okay, here we are.
And before we start, so we had Fermat's little theorem, lovely theorem. There is a little extension that we're going to refer to. There are even bigger extensions. There's a Fermat-Euler theorem, which is very interesting. But a sort of small extension is if n is a product of 2 primes, pq, and m is co-prime to n, then m to the power of p minus 1 times q minus 1 is congruent to 1 mod n. I think I'll ask you to take my word for that for now, but the Fermat-Euler theorem will provide a proof of that if you want to do some Googling around.
Something for the further reading notes.
Something for the
in the
YouTube
same
channel.
vein, we messed around some powers. We saw that sometimes you get the number 1. The idea that you could predict when that happens seems like reasonably plausible that you could do that even in this kind of case where it's the product of 2 primes.
Yeah. Nice. Right, let's
Okay.
get coding. Let's go. Okay, so what's going to happen? I'm going to try and send a secret code to James. Before I do that, we need some information from James. So why this is a very cool secret code sending algorithm is James is going to create some keys, not real keys, they're going to be numbers, and he's going to have some public keys, which are public information, but he's also going to have a private key, and that is top secret to him. And I need the public keys before I can send him a message. So we're going to try and do this top secretly, and I chat definitely won't be able to intercept this at all. Is the
Yes.
plan?
If we do it
Yeah.
right, then chat won't be able to steal our secret message.
No, no,
Okay.
we're going to demo this perfectly.
Right.
So James, I first need you to choose two primes, P and Q.
Okay.
Oh, keep them secret.
Oh God. Okay. Right. Yep. Okay. Yep. Secret primes. Secret primes. Chat. You didn't see
It's,
that. Okay. Yep. Secret
um,
primes.
and calculate n, which is the product of those two primes, and that is public knowledge.
Okay. So I tell everyone
Tell us
n.
n. Tell everyone n.
It's 143.
Amazing. And basically, part of the reason this works is that factorizing numbers into their prime factors is really hard. I guess n is quite small here, but in reality, these p and q will be like hundreds of digits long. It will be a very difficult task. So because we have no idea what p and q are, we can't work them out just from knowing n generally. But anyway, n's 143. James, we need you to calculate p minus 1 times q minus 1. And we only know n. We can't do that. We don't know what p and q are. So we couldn't possibly work out what p minus 1 times q minus 1.
There's people in chat who I think are already trying to hack my secrets. Possibly they factorized
Are we
143.
assessing?
Well, I'm going to secretly calculate this number.
Okay.
Don't look at my working out while I work it out.
Okay.
Yeah. Okay. Cool. Good.
I ignore that.
Good. Yeah. Good.
And I'm going to ask James to pick E as 7. That's another public key that we're all going to have. There is a condition on E. We need to make sure it's co-prime to James's secret number that he's just calculated. So I guess, James, you can confirm that. But that is a public number E. So as long as that criteria is met on James's side, then we're happy for that E to be shared. And the reason we want E to be co-prime to P minus 1, Q minus 1 is because we want to find the multiplicative inverse. We want to find the inverse of E modulo P minus 1, Q minus 1. So this idea of inverse is coming back again. And we want James to find this secret value D that's the multiplicative inverse of E. And I should say finding inverses is actually is a reasonably easy task for computers. There is a algorithm that exists for this, Euclid's algorithm. Finding inverses is actually fine. What isn't fine is knowing what p minus 1 times q minus 1 is. So we can't work out what d is. I don't know what d is. Chat won't know what d is because we don't know p minus 1, q minus 1. So we can't even start finding an inverse.
Yeah, so I do this secretly, I think.
Yeah.
Yes, good.
So
Okay.
D is James's top secret info.
Okay.
I guess there's a little note at the bottom about it's sort of another way to think about what this number D is. So if D times E is congruent to 1, modulo this thing, then it's one more than a multiple of P minus 1, Q minus 1. So I guess it's like short on time, but if you have a look at that sentence and see if you think that makes some sense. DE is one more than a multiple of P minus 1, Q minus 1. Anyway,
Okay.
right, my turn. I need to pick a secret message. If you scroll over to the right,
yes,
James, I've got some message options. I'm going to pick a message. Okay, I've picked one. This is this top secret. So then I know your E and N values because you made that public. So I've got my message M. I'm going to keep that secret, but E is 7. And I'm going to do some top secret calculations over here. I'm actually going to keep mine secret, James. I'm going to tell you that is congruent to 93.
Don't know what you mean. Okay, so you get 93.
Yeah,
And
that's modulo that n you sent. So I've done some secret calculations on my end. So the m I've picked gives me that.
okay. And that is quite hard for chat to invert, right? They can't do a kind
Yeah.
of power of 1/7
Yeah.
on the number
Of
93.
93. When you're in a modulo world, it's really a difficult challenge. And like even I'm not sure how to do that on my end. But it's James who's got a magic key that is going to help him in this task.
Yeah, so I now need to, I think I might use my computer to work out, I have to do 93 to the power of my secret decryption key, which
Yes.
is 103. But if I do 93 to the power of 103, possibly using some of the tricks from before, then I should get back to the message. I'm going to
You
try and work
should.
out 93 to 103 mod
Nice. Yes. There's
143.
there's a little calculation as to why this works, but like the what I've sent James is m to the power of e. James has got d that he can put it to the power of d times e. Well, we know there was a little note above that, so we said that de is congruent to 1 mod p minus 1 q minus 1. So de is 1 more than a multiple of that. And so we can sort of do some funky things with our powers and write it like this. And do even more funky things and write it like this. This is all just normal maths power manipulation. Um, and this step here is, I don't know if you remember that extension of Fermat's little theorem we had.
It was on the left, wasn't it? Yeah.
Um, so that is where we get the 1 from. And we end up back with an M. But it's very difficult to do that without knowing this secret D. And we've got no chance of knowing that D.
I've got back to, yeah, so I guess it's my knowledge. I know how often the pattern of powers repeats, more or less, or I know something about that. So where I am, you're somewhere through the pattern, but I know how to kind of complete the pattern, if you like. The actual maths is on the screen, but that's how I think of it, that I know kind of how the pattern's going. So this is actually 37 mod 143. Using my secret decryption number, which I think I did keep secret. I don't think I told chat it was 103. Which meant, how are you, James? Oh, thanks for asking. No one ever asks. I'm having a 5-star day, thank you.
The top secret message, definitely worthy of high-level maths encryption, I think.
Great stuff. I suppose I should have replied using a code. Maybe you would set up some primes as
Okay,
well.
I would have sent you something to send it back.
We can't use the same channel to communicate because Beth isn't allowed to know my primes. There's no need for me to tell Beth my primes. But maybe if I need to send you messages, then I need you to come up with some primes as well.
True.
I think that went very well.
Amazing.
For further reading, the place to find these, since someone asked in chat, is on the Maths Club homepage. There is a link in the YouTube description and a link kind of written on screen there somewhere for the Maths homepage. It's maths.ox.ac.uk/r/club. If you go there, there is a little further reading underneath each rectangle. They get posted at some point on the Friday, the day after the live stream, with some extra notes, bits of sometimes corrections or clarifications, if usually me has said something wrong. But I think that's where we're going to wrap up live stuff as well. You've got a challenge in chat as well. Maths2222 would like you to factorise an enormous number. I think they've picked larger primes than me. Possibly that's the one that you win lots of money for factorising. I don't know. Anything you want to say at the end, Beth?
No, all good. Yeah, I hope you enjoyed. That the secret code sending method we used is genuinely underlies a lot of encryption on the internet, but the primes used would be much bigger, like sort of 150 digits each kind of primes. But yeah, it's a really modular arithmetic is an awesome area of maths, and definitely do some more looking around on it if that interested you.
Chat says thank you to both of us. Thank you to Mario moderating chat. Thank you, Beth, for joining us and showing us modular arithmetic and secret codes, a little bit of RSA, plenty of challenges, lots of things to put in the further reading. We will see you, everyone watching at home and in chat and everywhere. We'll see you in about 167 hours for another episode of the Oxford Online Maths Club. But it's goodbye from me, goodbye from Beth. Have a nice evening. Have a nice weekend. See you next week. Bye from Mario in chat as well. There we go. Right. Bye, everyone. Now it's the awkward bit where I have to remember how to stop it. There we go. There. Done.